Okay, so let's start with some questions. And I think Nahi posted a question in Slack. Shall we start with that?
Yeah, I have a similar question to that.
Okay, so what is the reasoning? So Nahi asked, what is the reasoning behind the J3 eigenvalues being equally spaced? Okay, like are there eigenvalues at every unit step as shown through the ladder operator, but how do we know there aren't intermediate ones? Okay, so that's a good question. And so the idea is, we have to go back to a bit of linear algebra for this. So the linear algebra is, okay. So according to linear algebra, what we have is, if we have a collection of operators acting on some vector space, so this is some collection of operators, and so these are basically, you can think of them as matrices, okay? So these matrices don't commute in general, but suppose that a subset of these commute. So the subset of maximally, say, commuting operators or matrices. And that's some set, say, I don't know, like A1, A2, ... AN, okay? So then there is a procedure, and in linear algebra, which also takes into account the cases where there may be degeneracy. We did not get into degeneracy, but we might at some point. But there's a procedure in which you can construct. So now let's assume that these are Hermitian operators. Suppose that these were all Hermitian operators. Okay. So because this is a maximally set of commuting operators, you can construct simultaneous eigenbases, okay? And this eigenbasis is complete. And so meaning that, you don't have any state that is, say, not covered in this, eigenbasis. So, so how do we label this eigenbasis? We label it by the eigenvalues of these operators, say A1, A2, ... AN. Okay. Now, the thing is that because it's a complete eigenbasis, so that means that this is, the number of linearly independent. So the number of linearly, independent vectors the number is the same as the dimension of their Hilbert space. I've not proved any of this, okay? So that means that, this is like, these form these form an orthonormal. You can make them into an orthonormal set. So if I label them by an integer, or then, or well, a bunch of integers, right? A1, or they don't have to be integers, they're just numbers, real numbers, and then A1 prime, A2 prime, dot dot dot, AN prime. Then they will give you an orthonormal set. Okay. So from a point of view of linear algebra, you don't expect, I mean, there is going to be no more, vectors in this set. Like, they are not, these are the linearly independent orthogonal sets. And that's why, if you come back to the case in point where we are looking at applying JZ on LM, and we are saying, okay, it's giving me M, LM, and if I increase, J plus, what I'm getting is if I'm applying J plus on this, what I'm getting is some up to some constant, which is important, of course, L M plus 1. Okay, so it's so we are not going to get now if you remain in the confines of your algebra, there is no way of getting to a value of M which is between M and M plus 1. Okay? I mean, because this is a pretty easy set of operators. We basically have only 3 linearly independent operators, right? We have JZ, J plus, and J minus, right? So, so if you want to, so there is no other way. I mean, it's just that, you can try to come up with an operator which is going to increase the eigenvalue of M by, say, half, the JZ eigenvalue by half, but, you won't be able to, while still preserving the Lie algebra. I mean, there are some stupid things you can do, right? And the stupid things are, what if you apply some, even then, no, I don't think you can. Yeah. Given the fact that you have these things, the constraints that, these guys are, form an orthogonal set, from this set of operators, you can't really get to a value of JZ that is in between. So there might be some, theorem in linear algebra which, guarantees such thing. And I think the theorem is actually not in linear algebra per se. The theorem is actually in group theory. Okay. So these are what are known as the Curtin basis. So this is known as the Curtin basis. And it was Curtin who first classified all the Lie algebras, of which the angular momentum algebra is a particular example. And he showed that any Lie algebra, basically what is a Lie algebra? Lie algebra is a bunch of generators which satisfy, commutation relationship like this, but it's a closed, and they form the generators of a group, and there is and you can choose their basis to be such that they form an algebra like that, where f, a, b, c are real numbers. And and these are all Hermitian for the Lie algebras that we are interested in, the groups that we're interested in. And then these generators can be, Curtin showed that these generators can be divided into two groups. A set where they all commute with each other. Okay, so this is called the Curtin subalgebra, and a set and the rest who do not form this group. The rest comes in in even numbers. Curtin, you can show that, and those can be formed into complex combinations, and these are and these have form a kind of the E plus E minus alpha. They form some sort of algebra like this, and it's really that analysis by Curtin which basically showed what the possible spectrum of eigenvalues are for these H's. Okay. So I think sorry for the long-winded non-answer, I should say. But I think the thing is that in the simple case of angular momentum algebra, we can just try and fail, and to see that there is no other. You can start with, okay, there exists some generator, say J tilde, J prime, which is some some linear combination of J plus and J minus, right? Because if you're going to change the Jz eigenvalue, it has to be something of this form. And then you can show that the only way that you can reasonably change the J3 eigenvalue is really by only one. So you can prove that, I think, easily, although I have not done it, by making an explicit assumption to the contrary. But to get a more general flavor of things, you have to study Lie algebras and Lie groups. And even there, this question has not been asked. I mean, I have not thought about it explicitly before, but I think, there will be statements in the Curtin analysis where that would be a bit clearer. Okay. All right. So, Nahi, sorry, this is what I would recommend that you try. Okay.
Okay, sir.
Now you have another question, which is okay, before we move on to the other question, I think someone else also had questions, so let's take that. So I wanted to say, the topic that we covered in the last lecture was pretty difficult. It was pretty intense, I should say, not difficult. So I am in no hurry to get ahead without you actually sort of processing most of that information. But Shujosh, you had a question as well.
I mean, I had a question, but now think I got the answer. So I don't think I need to ask it anymore.